Last time we were talking about solving equations using factoring, using this technique of factoring. We talked about the zeros of a function, which are the x values that make my function have a y value equal to 0. And basically factoring was just utilized throughout. Factoring, we factored everything we possibly can, and we applied it to real world examples. In this particular case, we used a cardboard rectangular piece and we created a box out of it. But the idea is that we were able to figure out the volume as a quadratic function, and from that quadratic function we were able to factor it. So the idea was that we can factor equations, in particular quadratic equations, in order to solve the problem. So we've done a lot of factoring so far. And guess what? We're going to just do more of it. In particularly, we're going to do more of it when we talk about now what are called rational. So we're dealing with now rational expressions. So rational expressions, what are they? They're basically ratios, or I should say fractions, of polynomials. So for the longest, we've been talking about polynomials. We've been dealing with factoring polynomials, perfect square trinomials, quadratic expressions, right? And now we're just going to take that and add one extra thing to it, which is dividing them for fractions, ratios. And the idea here is, first we want to figure out how to find the domain. So I want to find domain of rational functions or rational expressions. So again, a rational function or rational expression are just expressions that are fractions, and those fractions have a numerator that's a polynomial and a denominator that's a polynomial. Okay, so an example, let's say I have a function g of x. Okay, this is our function notation, g of x, and the numerator is 3x plus 5, and the denominator is x plus 2. What do you notice? This is a numerator. This is the denominator. Both of them are polynomials. The numerator is a polynomial degree 1. The denominator is a polynomial of also degree 1. They're linear. I want to find the domain. So find domain of g of x. Now, remember what the domain of a function is? The domain of a function are all the x values of the function. Now, when we talk about the domain of rational functions, we're going to be concerned about what are the x values that are not in my domain. What does that mean? That means that there are going to be x values that make my function not work, quote unquote. Now, when does this function, what's like the bad, what's a bad scenario, quote unquote, for this function? Because it's a fraction, the denominator can never equal 0. So that's one thing you always have to highlight. The denominator can never be 0. Because there's no such thing as some number being divided by 0. We don't know what that is, so it's undefined. So to find the domain of g of x, I need to find the x values that make denominator equal to 0. So I need to find those x values. Once I find those x values, then I say what? I exclude the x values found in step 1 from the number line and include everything else. So that is what we're doing. To find what the good x values are, quote unquote, to find the values that are in my domain, I need to find what's not in my domain. So these are the bad x values. So the x values that make my denominator equal to 0 are going to be known as they're going to be the bad ones, bad. So of those bad ones, I'm going to exclude them. That's why I'm excluding them. And once I exclude them, I include everything else. So in this case, what's my denominator here? My denominator here is what? X plus 2. And I want to find the x values that make my denominator equal to 0. So all I have to do now is what? Set x plus 2 equal to 0. So x plus 2 equals 0. And what am I going to do now? Solve for x. So what is x? -2. Now pay attention to what I just found. I found the bad x value. This is bad. Why is this bad? Because this makes my denominator equal to 0. If my denominator equals 0, that means that my fraction has a 0 in the denominator, which would indicate that my function is undefined. So therefore, I must what? If it's a bad x value, I must exclude. Bad x value must exclude from domain. In other words, I look at my number line and I say of all the x values, there's one bad one. And that bad one here, I'm going to say, you know what? I don't want this. I don't want this x value being here. So I exclude. So if I exclude, that's the only one that's bad. So this is the only one. Only bad x value. I only found one. But everything else is okay. The numerator doesn't matter. It doesn't matter here. The numerator could be 0. There's no problem with the numerator being 0. There's a problem when the denominator equals 0. So I include everything else, but exclude -2. I include in domain. So then what's going to be my domain then? My final domain. I'm including everything to the left of -2. I'm including everything to the right of -2. I'm excluding -2. So therefore, my domain will be -infinity to -2 union -2 to infinity. And that's the idea, guys. So any questions about this? Does everybody understand what the task is to find a domain of a function like g of x? I'm finding all the x values that make my denominator equal to 0, excluding that from my number line and including everything else. And that's my domain. Okay, makes sense? Okay, what if I give you another function, f of x? And my function here has 2x squared plus 5x plus 2. And I'm dividing that by x squared plus 2x minus 3. Again, what I'm more concerned about is my denominator. It can't be 0. So what's my denominator? X squared plus 2x minus 3 equals 0. First, find those x values that make it equal to 0. So then what can I do here? Does anybody know how I can solve this? This is a quadratic equation. Can I solve this? I can factor. That's right, Jalen. Good. So I can factor this. And when I factor this, this becomes what? X plus 3, x minus 1 equals 0. So what adds to 2 but multiplies to negative 3. And then what happens? I get x equals negative 3 and x equals 1. What did I just find? I found bad x values. And there's 2 of them this time. Why are they bad though? They're bad because they make my denominator equal 0. If my denominator equals 0, then I have a fraction that's undefined. And so therefore my function is undefined when my x value is negative 3 and when my x value is 1. So then if I were to draw this out, I got negative 3 and I got 1. Open circle, open circle. Exclude those. That's why I put the open circle, but include everything else. So then my domain will be what? What's the domain of f? So my domain would be everything that doesn't include negative 3 and that doesn't include 1. So let me just say something above here before we continue. The domain here is an interval notation, right? Remember we talked about interval notation? You can also write the domain in set builder notation. So the set builder notation would be the following. It would be something like this. It would be like x, right? X and then the bar, x does not equal negative 2. So this here would be set builder notation. Again, these are equivalent notations. You should be able to do either or. Okay, so either or is okay. You should be able to do either way. So I'm gonna do both ways, okay? So I'm gonna do the interval notation. What's the interval notation here? It would be negative infinity to negative 3 union, negative 3 to 1 union, 1 to infinity. Boom. That's the one way of doing it. The second way is set builder notation. When I write set builder notation, I'm going to say it's all the x values such that x does not equal negative 3 nor 1. So you just put a comma. So again, you should be able to do either way. Either they ask you for set builder notation or they ask you for interval notation. Okay? So that's how you find the domain of a rational function. You find the x values that are not in the domain, which means that it's solved the denominator for 0, and those x values that you solve are the x values that are not in your domain, and so you exclude them but include everything else. So is that clear? Any questions about this? Okay, good. So another small thing, a small thing here is just to evaluate. How do we evaluate rational functions? And remember, the word evaluate just means plug in and find the numerical value of it. So if I have a function such as the following, so if I have f of x equals x minus 2 all over 2x squared plus 3x plus 8, and I want to evaluate f of 3, for example, all I have to do is plug in wherever I see x, I plug in 3. So this becomes 3 minus 2. Pardon me, I'm getting a call that I shouldn't be getting. So this is 3 minus 2. And then I get 2 times 3 squared plus 3 times 3 plus 8. 3 minus 2 is 1. And I get 2 times 9 plus 9 plus 8. So it's 1 over 18 plus 17, which is 1 over 35. So again, this idea of evaluating a function is the same thing applied to rational functions or to any function. You plug in wherever you see the x value, you plug in the numerical value that you represent, that x is representing. So in this case, my x value is 3. So every single time I see x, I just plug in 3, and then I perform PEMDAS, and I find the numerical value. So f of 3 is equal to 1 over 35. So that's the idea behind evaluating. But the more interesting thing now is simplifying rational expressions. So this idea, remember I've mentioned in the beginning of the semester, it's on your syllabus. So you want to, from this course, you want to take away 3 important skills. One of them being factoring. The other one is simplifying, and the third one is solving. So those 3 different skills are the kind of skills that you're going to master, hopefully by the end of the semester. So we want to simplify rational expressions. What does that mean? So if I have an example, again, a rational expression is just a fraction or a ratio of polynomials. So if I have something like this, 3y minus 12y squared, and all of this is divided by 3y. I want to simplify. So from now on, all I'm going to be doing is simplifying, simplifying, and more simplifying. And again, the name of the game throughout this whole thing is factor, factor, and factor. So the question is, when you say simplify rational expressions, my question will immediately be, can I factor? And if so, what does it factor into? So the numerator, can I factor that? The denominator, can I factor? Well, the denominator here, I can't really do much. It's just 3y. But can I factor the numerator? 3y minus 12y squared. Is that factorable? How do I factor such a thing? So wait, Yim asked the question 5 minutes ago. Pardon me, Yim. Yes, you do include negative 3 to 1. You do. You just don't include equals negative 3 equals 1. You don't include those 2 points. But you do include everything else. So you do include what's in between negative 3 and 1. So sorry about that. I didn't see your question. So Jalen says yes. So then what is what does the numerator factor into? Or how would you factor the numerator? You can use what?
You take the common 3y.
Yeah, you can take out a 3y. You don't have to take out a negative. You can if you want, Jalen, but you don't have to. You can take out a 3y just as that. And you get 1 minus what? 4y. And then what do you notice? The 3y and the 3y, right? This is a multiplication in between. So the 3's here, I can cancel the 3's. And the y's I can cancel. I can do that. I can divide them. And what's left is 1 minus 4y. And this is the simplification of 3y minus 12y squared. So what did I perform here? I performed a GCF factorization. Like this is the first one we studied, right? The first kind of factorization technique, GCF. And you see how we learned about these different factoring techniques, and they're going to come right back again and again. Okay, let me give you another one here. 24 r cubed t squared plus 36 rt to the fourth. And I'm dividing this by 12 r cubed t plus 18 rt cubed. So what's the question here? Can I factor the numerator? Can I factor the denominator? That's all it's going to be, guys. Simplifying is factoring, essentially, and canceling if possible. So can I factor the numerator? So there is a GCF for the numerator and for the denominator. What can I factor from the numerator? Among the 24 and the 36, what's the common factor or the greatest common factor? It should be a 12, right, Jasmine? So you can take out a 12. You can take out a 12. You can take out an r. Remember when we look at the variables, we always take the smallest exponent. But there's also the t in there, right? So I can take out a t what? I can take out a t squared, actually. That's my GCF. And when I do so, what's the result? What's left over? I'm left with a 2. I'm left with a r squared. And I'm left with just a 2r squared. And I'm going to add this. I'm left with the 3. The r is taken out. And I'm left with t squared as well here. So that's the result of factoring out the GCF in the numerator. Let's look at the denominator. Among the denominator, what can be factored out? I can factor out a 6. I can also factor out a small r, and I can factor out 1t. When I do so, what's left? I'm left with 2r squared plus 3. I'm taking out an r and I'm taking out a t, so this is t squared. Now look what happens. What do I have here? In the numerator and denominator, I have two expressions that are identical. Because they're identical and there's multiplication on top and you're dividing it, then you can cancel these or divide them out. When you divide them, you're left with a 1 and a 1. So what's left in the numerator is a 12r t squared. And in the denominator, it's a 6r t. And this cancels even further, right? The r's here cancel. Boom, boom. The t's cancel. I'm left with 1t. And the 6 goes into 12 twice. So what's left? 2t. So all of this that we started out with, this rational expression here, simply reduces after we take the GCF on numerator and denominator and cancel things out. We're left with a 2t. That's it. So again, simplifying rational expressions, factor, 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 and more factor. That's all we're going to be doing, factoring, factoring. And this will occur again and again as we progress into this world of rational expressions. So now look what we have here. What do we have? We have two trinomials, numerator and denominator. And the question is, can we factor the numerator and denominator? So is x squared minus 7x plus 12. Can I factor this? Or what does it factor into? So in a way, this is a bit of a review, right? I know it's been a long week. Nice break. We're back. So what does the numerator and denominator factor into? So what multiplies to 12? Positive, but adds to negative 7. What multiplies a positive 20, but when you add it, gives me negative 9. This should be quick, right? So Jalen, that's right. The numerator will be x minus 4, x minus 3. That's the numerator. And what would be the denominator? What multiplies a positive 20 but adds to negative 9? So they both had to be negative in order to get a positive number, but when you add them, give me a negative number. Anybody. X squared minus 9x plus 20 can be factored to what? X minus 4. Thank you, BB. X minus 5. That's right. Great. So we factored the numerator and denominator. That's the hardest part. And then once we have that factored, what do we notice? There's an x minus 4 in the numerator and x minus 4 in the denominator. That's nice because now what happens? Those things cancel because you're dividing them. They're the same. So this becomes a 1, this becomes a 1. When you divide two things that are the same, it becomes a 1. And what's left? X minus 3 over x minus 5. And I'm done. Okay? So that's the idea. And more of this is to come. We're just factoring as much as possible in the numerator and denominator. Let's see. What if I have 2x squared minus 5x minus 3, and I have this divided by 2x squared minus 3x minus 9. Now, again, I want to simplify. So all of these are about simplifying, which relates to factoring and seeing if things cancel. So can I factor 2x squared minus 5x minus 3? Now remember, for this one, you can't just find two numbers that multiply to multiply to negative 3 and add to negative 5. You have to do an extra few steps. Remember, the few steps is what? The 2 and the negative 3. This gives me negative 6, right? And then my question is, what multiplies negative 6 that adds to negative 5? Do you guys remember this? So we look for two numbers that multiply to negative 6 but when you add them, give me -5. And then you replace that middle term by -5. So -3 and 2, that is, remember, that multiplies to -6. So the problem with your suggestion, Jasmine, is that both are negative. If you have two numbers that are negative, then they give you a positive number, but we want negative. So Sierra says -6 and 1. So if you multiply -6 and 1, you do get -6. So that's good. -6 times 1 does give me -6. And then -6 plus 1 does give me -5. So I do rewrite this as 2x squared minus 6x plus 1x minus 3. And then what do I do here? I factor, right? I factor the first group. When I factor the first group, what do I get? I get 2x, x minus 3. And the second group, I can't really factor anything, but I'm factoring a quote-unquote a 1 out. I'm just left with x minus 3. So then when I recognize the x minus 3's here, I'm left with x minus 3 multiplied by 2x plus 1. So boom, I factored x minus 3 multiplied by 2x plus 1. So I did the first one. How about the next one? 2x plus 3, x minus 3. Wow, that was quick. That was quick. That's right, guys. This should be quick. You should be looking at these now and saying, oh man, I know how to do this. Easy. So -18, right? 2 times -9 is -18. What's numbers multiply -18 but add to -3? Well, one of them has to be -6. The other one has to be a plus 3x minus 9. And then you can factor the first two, factor the last two, and I get 2x, x minus 3 plus 3 times x minus 3. And that equals x minus 3 multiplied by 2x plus 3. That's exactly right. And now what happens with the x minus 3 and the 2x plus 3? What happens? The x minus 3's here both cancel. Boom, boom. They cancel. And then what's my final result? 2x plus 1 over 2x plus 3. That's my answer. Now, please, I beg you. I'm begging you because a lot of people make these mistakes, okay? So I should not say no, I should say warning. Let me take this example here, 2x plus 1. And let me just warn you all. This is not true. Just because you see two expressions that are the same in the numerator and denominators does not give you the right to cancel them out. You have to be a little bit more careful. Ask yourselves, why is this possible? Why is this permissible? Why is this permitted? But this is not allowed. So that's something you should think about. Why can I factor out these two numerator and denominators? And I recognize, hey, there's an x minus 3 and x minus 3, and I can cancel those out, no problem. And everything's okay. But the moment I see 2x in here, 2x in here, I cannot do that step, apparently. Well, one thing is, the real reason why is that you are circumnavigating the sequence of PEMDAS. You're saying that you can do division before you do parentheses, because in reality, when you have 2x plus 1 divided by 2x plus 3, in reality, it's really like this. It's really written this way. But we don't write it because it's redundant. It's really 2x plus 1 parentheses divided by parentheses 2x plus 3. Do you see that? Yeah, Jalen, one simple response would be one is multiplication, the other one is addition. But why does that why does that matter? It matters because in this scenario here, you have 2x plus 1 is an expression together. It's one single expression, and that's, in a sense, it's around parentheses. It's around the parentheses. It's within the parentheses. And the same thing happens for 2x plus 3. So if you were to say, hey, you know what the 2x's, let me cancel them. What you're saying is that division comes first, then parentheses. But according to PEMDAS, parentheses comes first, then division. So that's why this is not permissible. It's because of PEMDAS. So remember PEMDAS. This is first. Parentheses is first. And if you notice here, what do I have? I have multiplication, division, multiplication, right? I have a multiplication of two things here, multiplication of two things here, and they're both being divided. Remember with PEMDAS again, the multiplication and division, they could be interchanged. They could be swapped. So that's the reason why if you have this multiplication here and then multiplication here, I can, in a sense, say, hey, you know what, let me divide first because of multiplication and division here. That's the reason why I can cancel out the x minus 3's and not sweat it. Again, just because you see two things that are connected to one that are the same across the division sign here, it does not mean you can just, hey, let me cancel it. No. All right? Just make sure that's clear because I'm pretty sure it's bound to happen. It happens every time. It's like almost a guarantee. I'm just letting you guys know. Okay, something like this. What if I have 8x cubed minus y cubed divided by 4x squared minus y squared? Again, factor. Can I factor? How do I factor? So what is the numerator an example of? And what's the denominator an example of? What factorization case is the numerator compared to the denominator? So whenever you see those 3's as exponents, right, you should think of what? And whenever you see those 2's, you should think of what? When you have the 3's, it's a three-dimensional, it's a cube. So the numerator should be a difference of what? Difference of cubes or perfect cubes. And the denominator here, the 4 is a perfect square, x squared, y squared. So this is a difference of perfect squares. So how do you factor the denominator? 4x squared minus y squared. Four x squared minus y squared is factored into what, guys?
Is it 2x minus 2y?
It's 2x plus y
Plus y.
Times 2x
Minus y.
minus y. So remember, this comes from a squared minus b squared equals a plus b, a minus b. So in this case, my a is the 2x and my b value is the y. Okay, so that's important. And now the next one, the numerator, 8x cubed minus y cubed. So first of all, you have to remember what's the difference of perfect cubes. Difference of perfect cubes. What does that look like? So it's a cubed minus b cubed equals a minus b, a squared plus ab plus b squared. So in this case, I got what? Very good, BB. Good. So this is 8 cubed, 8x cubed, which is really what? 2x parentheses cubed minus y cubed. And all I have to do is plug in the formula. So I get 2x minus y, parentheses, 2x parentheses squared plus 2x times y is 2xy plus y squared. Now remember, 2 parentheses x. The 2x is in parentheses and I square it. So really I got 2x minus y raised to the 4x squared plus 2xy plus y squared. So I can rewrite this as 2x minus y, and I get 4x squared plus 2xy plus y squared. Now, what's the thing that's the same? The 2x minus y's. Those cancel immediately. Left with the ones. And then the result here is that in the numerator, I get 4x squared plus 2xy plus y squared. And I divide this by 2x plus y. And that's my final answer. So guys, you have to know difference of perfect squares. You have to know difference of perfect cubes. You have to know sum of perfect cubes. You understand? So all these factoring techniques were not just to learn about factoring for the sake of it. Now we're using this on a more consistent basis now. Okay, so let me give you one last one of these. So we're gonna try to see every single scenario possible for factoring. And I think this is a pretty good one. So this is x to the fourth plus 3x squared plus 2. And all of this is being divided by x to the fourth minus 1. So I want to simplify this. What does the numerator look like? What is the numerator an example of? And what is the denominator an example of? That's the first thing you should be able to identify. Let's start with the denominator. The denominator is x to the fourth minus 1. What is this an example of? What kind of factoring scenario or case is this? There's a minus sign, so this indicates some kind of difference. Yeah?
Is it the difference of perfect squares?
It is. It is difference of perfect squares. So then that means I can rewrite this as a difference of perfect squares, which would mean that this is x squared squared minus 1 squared, correct? So that's the difference of perfect squares. And when I factor this, remember, this goes back to this. Difference of perfect squares, this factors into what? X squared minus 1, right? Is that what you're going to say?
Yeah, I was gonna say the answer, but it's okay.
No, go ahead. X squared minus 1, and then what's the next thing?
X plus 1, x minus 1.
X squared plus 1. But then where did you notice? You notice that this can be what? So the thing is here, you're factoring difference of perfect squares twice. So this is like the first time you do it, right? From here to here, it's the first time. And then you say, hey, this here can be factored once more because this is also a difference of perfect squares. So this is when you factor completely. You see that? So you're applying the difference of perfect squares twice. So this becomes x plus 1.
X plus 1, x minus 1.
Yes. And then you have the x squared plus 1 tagged along with it. So now this is complete. X plus 1, x minus 1, x squared plus 1. But right, David? This is not factorable. Okay? So be careful, guys. With the plus, when you have squares, there's no such thing as a factorization, at least not in this scope of the course. You can't factor x squared plus 1 or a sum of perfect squares. But you can always do a difference of perfect squares. So that's the denominator. How about the numerator? The numerator seems a little bit more tricky, right? X to the fourth plus 3x squared plus 2. Remember what happens when we have something in this form? Where the first term is the second term just squared. Remember what we do when we have situations like this? What do you notice? If I write this using a different color, how can I rewrite this? This becomes really what? If I say let x squared equal to u, look what I get. I get u squared plus 3u plus 2. This is an example of what? Of a quadratic form. It's not necessarily quadratic exactly, but it has a quadratic form to it. Now, can I factor this as a quadratic? U squared plus 3u plus 2? Definitely. What multiplies to positive 2? That gives me plus 3. Well, it's going to be what? It's going to be what? U plus 1. And it's going to be u plus 2. But of course, we're not dealing with u's. This u idea, it just came out of almost like my imagination. I originally have x's in them. So then I have to put back what u originally was equal to, which is x squared. So I write x squared plus 1 and x squared plus 2. So that's going to be the factorization of the top. You see that? Does everybody see that? Any questions about this? I know we went over this last time, but this is one of those factorization that people tend to forget because it's not so commonly, that doesn't happen so commonly, so common as the other ones, but it's still a technique you should know. And so now that you have that, x squared plus 1s, those are the same. They cancel. And what's left? The only thing that's left in the numerator is x squared plus 2. And what you have in the denominator is x plus 1, x minus 1. Okay? Everyone clear with this? So that's the name of the game, guys. We're just factoring and simplifying, factoring, simplifying as much as we can. All right. So once we understand this whole simplification process of rational expressions, we're gonna just tag more stuff onto this simplification. And in particular, we're gonna be talking about multiplying and dividing. Multiplying and dividing. Rational expressions. Normally, you might think, wait, but shouldn't we add and subtract first? Because isn't that like the simpler operation, right? Isn't subtracting and adding simpler than multiplying and dividing? Well, actually, in this field of rational expressions, it's actually easier to multiply and divide than to add or subtract. And you'll see why when you talk about adding and subtracting. But multiplying and dividing is actually the easier of the two, easier of the four operations. Okay. So what does that mean? Well, it just means that we have now two fractions. And these two fractions are 16y are polynomials again. But in this case, we're multiplying them. Okay. Now, does anybody remember how we multiply fractions? How do you multiply two fractions together? Just in general. Like, for example, if you have
27 multiplied by 20
uh-huh.
and a square multiplied by a square, b5, x squared, y3, and in the bottom there it will be 16 multiplied by 9, and then x, y squared, a squared, b.
Yes. So you're right. You're right. You're literally saying you're multiplying the two things across, right? You're just taking everything on one side and just multiplying everything with the other thing on the right side, and so on and so forth, right?
Excuse me, Professor.
Say it again.
Can you maybe like try simplifying it first before you go and multiply?
And that's what I was gonna say. Yes. So let me just give you a small example, okay? A smaller example. Let's see. If I have 45, like 45 over 14, multiplied by 7 over 9. Okay. So when you have fractions like this and you want to multiply them, the first your gut feeling would be, oh, let's just multiply across. I have a calculator. It's all good. But what's nice about having fractions and you multiply them is the possibility that there are common factors among the numerator and denominators. So you start to see, wait a minute, the 7 and the 14, they're both common factors of 7. The 9 and the 45 are both common factor. Greatest common factor is a 9. So what you can do before you multiply is you can actually cancel, if you can, before. Now look at this. I can cancel the 9 with the 45. I get a 5. The 7 and the 14, this becomes a 2. And look how simple my computation becomes. It's 5 halves. If you did it the other way, what would you have gotten? You have gotten what? 45 multiplied by 7 is 315. That's if you did 45 times 7. And if you did 14 times 9, you get 126. Then you have to be like, okay, what divides 315 and 126? What's the common factor, right? Or if you have your calculator, you can actually compute 315 divided by 126. And what do you get? 2.5, which is exactly what? 5 halves. So do you see the usefulness of simplifying before? So try to see always if you can simplify before. If you can't, then you just multiply across. but always try to simplify before. So what do you notice? 9, 27. And again, these numbers have to be, one has to be below in the denominator and the other one has to be in the numerator. So 9 divides 27 3 times. That's good. The a squareds here also cancel out. Awesome. The b here divides b to the 5 once. So I have b to the 4th now. So far, look what I have. I got 3 b to the 4th. That's simplified. And in the bottom here, I only have a 1 because everything else is canceled out pretty much. Then what happens? The x's here cancel with one of the x squareds here. The y squared goes into y cubed once. So far I got just an x and a y. And then look at the 16 and the 20. What can I factor out from the 16 and the 20? Well, 16 and 20 both have a common factor. The greatest common factor is a 4. So this becomes a 4, this becomes a 5. So look what I get. I get a 5 here, and I get a 4 here. Look how much simpler now my computation becomes. And now I can cancel, I can multiply across now. So 4 times 1 is 4. 3 times 5 is 15. And I get b to the 4th xy. Okay, guys? So you would have gotten the same answer if you would have just multiplied things out like that across first without simplifying and then simplify at the end. But hopefully you start to realize how much work has been averted from being done if you were to simplify first. So I would suggest always simplify, simplify, simplify beforehand, and then you multiply across. So note, simplify first, and then multiply across. So that's the general tip. So I'll give you another one of these just to drive home the point. So we get 15x squared y to the 4th. And I got this over 24 ab cubed. Multiply that by 28 a squared b to the 4th all over 35x y to the 4th. So again, can I cancel things beforehand? I can. The a's here cancel with one of these a's. B cubes cancel here. This is just left with the 1. The y to the 4th, y to the 4th. The x is here, the x is here. 15, this becomes a 3 because I can divide this by 5. And the 24 and 28, I can divide by a 4. This becomes a 7. This becomes a 6. So you just be careful with the cancellation here. The 7s here also cancel out with the 7s here. And the 3 here becomes, the 3 over 6 becomes a 1/2. So I did a lot of cancellation beforehand, right? What's left in the numerator here? The only thing that's left in the numerator is an x, an a, and a b. So you get xab, and the only thing that survives the denominator is a 2. So I get divided by 2. And that's my final answer. xab over 2. Okay. So if possible, cancel, cancel, and cancel. Okay. Of course, we're not going to have just these kinds. We're going to have of multiplication. We're gonna have other kinds. We're gonna have where we have to actually factor. So for example, if I have 3x minus 5 over 4x squared minus 2x, so all of this stuff here just becomes more factoring for you. That's why your factoring skills have to be on point. So you see here, I wanna multiply this out. I wanna simplify. So again, simplifying, if possible, can I factor? So 3x minus 15, I can factor to what? 3x minus 5. 4x squared minus 2x, I can factor this as 2x. This becomes 2x minus 1. 20x squared minus 10x, I can factor this. It becomes 10x, x minus 1. 15x minus 75, I can factor 15, and this becomes x minus 3. No, actually, no, it's not 3. It is 5. Does everybody see that? All I did was I factored the numerator, denominator, numerator, denominator. And then what do? I'm not going to multiply things out yet. I'm going to see, hey, what can I factor out? What can I cancel? So x minus 5 here, boom, goes away with the x minus 5 here. That goes away. What else goes away? I got one little x here, goes away with one little x here. What else goes away? Well, the 2 goes into the 10 5 times. The 3 goes into the 15 5 times. And what else happens? The 5s here also cancel out. So I've canceled everything out, and I'm left with what in the numerator? The only thing that's left untouched, unscathed, is the x minus 1. And the only thing that's by itself here in the denominator is the 2x minus 1. And I am finished. Make sense?
I have a question.
Yes.
Shouldn't it be 10x parentheses 2x minus 1?
Oh, yeah. Thank you, Jasmine. You're right. You're right. It should be 2. Thank you. I would have just went away my merry way and thought, yeah, this was all correct. So this changes our whole answer, doesn't it? So if it is 2x minus 1, what else happens? I got 2x minus 1's canceled out as well. So what's my final answer? Jasmine, what do you think my final answer is? You're right. It is a 2x minus 1. So then because of that, what's the final result? If everything cancels out, what's left? 1. Wow. Nice. Nice. Very good. So thank you. Yes, that is correct. 2x minus 1. So everything cancels out, guys. If everything cancels out, you're not left with a 0. When you cancel, it means that you're dividing something by itself. So when you divide something to itself, you're left with the 1. So the answer here is 1. Good. Okay. Okay, let me give you a heavy one. All right, this will be the last one for today. So what if I have x cubed minus y cubed? And I get 2x squared plus xy minus 3y squared multiplied by 2x squared plus 5xy plus 3y squared. And this is x squared plus xy plus y squared. My goodness gracious. So look what we have here. We have a couple things to worry about, right? So the numerator here, what's the numerator here? Difference of perfect cubes. So this becomes immediately what? X plus, no, pardon me, x minus y multiplied by x squared plus xy plus y squared. And you should already start to see, hey, wait a minute, look at this. X squared plus xy plus y squared. This is also can treated as in parentheses. And you notice, hey, wait a minute, this is the same thing as this. So you should already immediately know that these here will cancel out immediately. Okay, now the more of the work, the bulk of the work here deals with this kind of trinomial and this kind of trinomial. So this becomes what? 2x squared plus xy minus 3y squared. It's a quadratic in nature, trinomial. The same thing applies here though. 2 times negative 3 is negative 6. What adds to negative 6? But what multiplies negative 6 but adds to positive 1? And we did this already. This becomes 2x squared plus 6xy minus xy minus 3y squared. So then I factor this, and I'm left with 2x. This becomes x plus 3y minus y. I'm left with x plus 3y again. And this becomes x plus 3y multiplied by 2x minus y. So that's what the denominator here will look like. It will be x plus 3y parentheses 2x minus y. And then I have to take care of this one here. So I'm going to just treat this, call this 1. I'm going to call this 2 here. So 2. Yeah, and this is 1 here. And I'm going to have to do with 2. So what is 2? 2 is 2x squared plus 5xy plus 3y squared. Again, 2 times 3 again is 6, right? What two numbers multiply to positive 6 but add to positive 5, and they have to be 2 and 3. So this becomes 2x squared plus 2xy plus 3xy plus 3y squared. And now I have these two fractions, two groups here. I could take out the 2x, and I'm left with x plus y. I can take out the 3y, and I'm left with 3x plus y. Sorry, this should be just an x. And now I can factor out the x plus y, and I'm left with x plus y multiplied by 2x plus 3y. So this becomes x plus y times 2x plus 3y, right? Okay. Let me just see if everything works out. It looks right. And then what cancels out? The x plus, wait a minute. Something seems to be off. Is something off here, guys? Yeah, you guys can probably see it before I can. 3x minus 6. Oh. Does anybody see it, or is it just me? Yeah, I think everything as of right now, I may be missing something, but this is minus 6, right? So then this should be a positive. Oh, Guys, this is not correct. This is correct, but this is not correct. Why not? -6, right? 2 and -3. -6. What multiplies to -6 but adds to +1? It can't be 6 and -1. So that was my mistake. This should be +3, and this should be -2. So this is going to change a little bit, just a little bit. So what's going to factor out from here? An x, and I'm left with 2x plus 3y. And what's going to factor out from here? A -2y. This is, sorry, a -y. So -y, this becomes 2x plus 3y. So now we're talking. So now this becomes 2x plus 3y, x minus y. So the only thing that changes here is this is an x minus y, and this should be a 2x plus 3y. And so now we have more things that cancel out. The x minus y is canceled, the 2x plus 3y is canceled, and the only thing that's left is the x plus y. And finished. Okay. All right. So we've done a lot of factoring, simplifying of rational expressions.